دكتور اسمح لي بس حاجه بسيطه نقدمها لك بدايه السيمينار. حقيقه شهاده شكر وتقدير للدكتور محمد من الجمعيه السعوديه للعلوم الرياضيه على حقيقه جهوده وانشطته خلال الفصل الدراسي، وحقيقه على كثره مشاغله وكثره يعني نشاطاته الاكاديميه، الا انه حقيقه يعني مبادر في السيمينارات والانشطه. حقيقه كلمه شكر فقط يعني لا تعني الا رمز تقدير، والا يعني الدكتور حقه علينا اكبر واكثر، ونعرف انه ما ينتظر منها شيء ولا ينتظر، لكن هذا حقيقه رمز. كنت شرف حقيقه دكتور نقدم لك هذه الشهاده.
جزاك الله خير.
على ربنا يصبر. يعطيك العافيه دكتور، وانا حقيقه ما اقدر احضر من عندي والله يعني استمع. الله يحفظك.
بارك الله
شكرا
فيك.
جزيلا.
بارك الله فيك. So we continue our series of lectures on stochastic calculus, stochastic differential equations, and so on. So today's lecture we will focus on applications of this formula and show you the main result of the existence and uniqueness of solutions of stochastic differential equations. So let's get started. So first of all, we have to discuss what is around stochastic differential equations, what kind of solutions we have, different definitions of notions of solutions, and then we need some other definitions to introduce in order to be able to define the framework of analyzing stochastic differential equations. So first of all, in the theory of stochastic differential equations, we require some properties of the solutions, such as some measurability property, continuity, and so on. So we need to introduce the notion of filtrations and the notion of measurability or adapted process or adapted solutions. So I consider here is the first definition a family of sigma algebra, a family of sigma fields defined on some probability space, omega fp. This is a space with this probability measure, and then ft is a family which is included in the whole sigma field f. And a filtration is just an increasing family satisfying this inclusion property with the spot here. Fs is included in Ft as soon as S is smaller than T. Okay, so this is the notion that we need in discrete formulation also can be described in the following way. Okay. The second definition is adapted processes. So a filtration is usually linked to some processes. We have to understand somehow how can we construct such families, such filtrations. So what we do is we consider a family of random variables indexed by time, as you can see, called stochastic process. This is from now. I call a stochastic process a family of random variables indexed by time, and then as soon as I need some properties, I will add it. Okay, so what we do is we consider the sigma algebra generated by this random variable at ht. Consider sigma algebra generated by a measurable function. Now at each time I have yt as a random variable, and I consider the sigma field generated by this random variable. This is just the simple family you can construct with this. And now I would like to get more information. For if I stop here at time t, this is not enough for me. I need more information. So what I do, I consider the sigma of ys, and s is less than t. Now my family become rich. I have more information on that, right? So this is a way to construct this family ft as the sigma algebra generated by all the random variables indexed by S, and S is less than T. So this has many applications in modeling, in actuarial sciences, in finance, in information theory, in population dynamics. I will give some examples on that. So this FT refers to all the information we have on the system up to date. This is the model. Okay, so I don't need for the moment the discrete time. So this family is a sigma, is increasing in time, and it is a sigma algebra. Okay, let's now see some examples of some processes that are adapted to the filtration. So once you take the family like this, so by construction, your process Y is adapted to this filtration. So we call it its own filtration, or the filtration generated by the process itself. So by construction, the process X is measurable at each time. It is XY is measurable to FT by construction, right? So let's see, for example, if we take a Brownian motion, B and FT denotes the corresponding filtration. I mean by FT, the filtration generated by B itself. Right. So now, examples of processes that are measurable to this one. If I take a smooth function F on T and space, and I take the composition, the transformation, Xt is alpha of T Bt, then this function is adapted to the filtration Ft. Bit Xt equal to Pt itself. Pt square minus T. Okay? The supremum up to time T of Bs is adapted to the filtration. The maximum of P squared. The infimum. Yes.
Here Xt is adapted to Ft, whatever F. I mean for any F, for any small F.
Yes. This one, you mean this one?
Yeah.
Yeah. Because F is deterministic. There is no randomness in F. You have T and small x. But deterministic function. I just put
on F, it's okay.
Yeah, C2. Oh no, whatever. No, we don't really need smooth this on F. As soon as you can take even F measurable function on T and S. Because if I am not interested in the decomposition of FTBT, I don't need regularity.
I mean, if you remove the measurability of F with respect to
no.
Yeah,
I should.
Because here you say where F is a function of two variables, so it's adapted. This might.
Yeah. It should be measurable with the two. At least measurable with the two parameters. Yes, space and time. Okay, so you have the maximum and the minimum. Now let's see what is not adapted. An example for what is not adapted is, see this one. You have here xt bt plus 1. As soon as I shift more than t, it is not adapted. Right? So the same here. If I take something which depends on the future, this is capital T, the future, greater than t. As soon as you take, this one is measurable with respect to ft, but this one not. This is the future. So this is not adapted to the filtration of the Brownian motion. Okay, that's great. So I call a stochastic process is adapted to its natural filtration ft. That is why is measurable with respect to, is a functional of bt. That is why, what does this mean? This means that yt is a measurable functional, is a functional of the whole path of bs up to time t. Okay? Good. So this is, if we consider now a Brownian motion, the corresponding sigma algebra of bt is denoted by the sigma of bs less than t. Okay, so that is what we have discussed already. And now, if we consider, this is something interesting. I consider xt equal to bt square, right? So the natural sigma algebra generated by bt square is given by this one, right? By gt, sigma of bs square is less than t. Now, this xt is adapted to gt and ft. Why? Because this is a transformation of bt. This is a function of bt. So it is also measurable with respect to the f. But the problem is, and this sigma algebra is included in this one. Okay, so for example, we can reconstruct the whole information from the absolute value of b on bt square, but not about bt. I cannot get information on bt. Okay? So this is the problem. We cannot say anything about bt from bt square or from the absolute value of bt. So for this reason, the information, the measurability is a very important. Okay, there is some situation where we can use those information I speak about. So you have, for example, market information and information on histories. You have share prices, exchange rates, interest rates. All this can be modeled by solutions of stochastic differential equations, which are driven by Brownian motion. And of course, those solutions are then functions of Bt or functionals of Bt, and we will see some examples in this setting. Okay, so let's get started. What is the problem of stochastic differential equations? You consider as, take this B in equation 2(1), take sigma is equal to 0. So you have an ordinary differential equation, right? You have dxt is equal to bt xt dt. And now if we add this perturbation with respect to sigma and bt, you have what we call a class of stochastic differential equation. So if we consider some very particular cases where you take sigma is equal to 0 and b takes this form, so you have a linear equation which has these solutions like this. Okay, so now if maybe we can speak about some heuristic motivations of this equation 2.1. So if you consider some increment xt, the difference between xt plus delta t with xt, so you see that this is can be written in terms of, sorry, the spot doesn't work. Yeah, it can be decomposed. That difference I showed you before can be decomposed on the sum of bt xt delta t and this term sigma t the xt and delta bt. Okay, so of course once you take this difference very small, you write it in this infinitesimal form, and you know some information about the distribution of this term and this one. So this is the mean. This one corresponds to the mean, and this one is the variance of this equation. So it is more appropriate in the theory of stochastic differential equations, since we have less regularity, to have integral representation formulation of the equation. So we generally look for some processes x which satisfies this equation 2.2. This is what we call stochastic differential equations. So we will discuss now what are the conditions on existence and uniqueness and some other properties of solutions, but maybe I will not have time to explain more properties on that, but I will just give some main results on existence and uniqueness, and give some examples, of course. So let's start by to announce the result, and then go over some examples, and then at the end I will give the proof of this result. So as usual in any differential equations, you require these conditions here, which are Lipschitz conditions and nonlinear growth conditions on the coefficients. Very classical, right? And you see here that are uniform, the bonds here are uniform in time. But we can put some time dependence here and add in some condition on integrability on time and so on, but it is not so important for the moment. Okay, so my initial condition can be a random variable. Okay, and this random variable should be measurable to the initial sigma algebra, which is if not. Okay, that's what we need. Okay, so under these assumptions here, you see that everything is deterministic here for the moment, and the initial condition is random here, and the source of randomness comes from Bt here, from the Brownian motion, right? So under these conditions here, add in this property, square x naught is square integrable as a random variable, so there exists a unique, continuous, adapted solution to this equation which satisfies this property.
I have a question.
Yes, please.
F naught, what's F naught?
If not.
Ah,
Yes, yes. So this means that the sigma algebra generated by x naught,
That's it.
right? Yes, that's it. But A can enlarge somehow this if not, to contain some other events with probability 0. This is called the notion of completeness. I can complete a sigma algebra with other measurable sets with measure 0. Okay? So for the moment, let's keep it as the sigma field generated by x naught. In many situations, this x naught, this if naught, is a trivial sigma algebra. It contains only omega and empty set. Yeah, trivial sigma algebra. In many situations. Okay? So our solution should satisfy this integrability condition here, and then it should satisfy equation 2, this one. Okay? Good. So maybe I would like to discuss here what is the notion we are looking for here, notion of solutions. So we the notion I'm dealing with here is called strong solution. Why strong solution? Because I require that the solution will be adapted to the filtration generated by the random source here. So this is mainly, I have a Brownian motion, and I have its own filtration. So this is the input. And the other inputs are x naught, the drift b, and the coefficient, the diffusion coefficient sigma. So we have 4 inputs, right? Now at the output, so this inputs goes through the equation 2, right? I enter them in this machine, and after, with this transformation, I will get something. When there is a solution, I will get something, right? So this object I can get at the end. I can say in these situations that the result, the x I get, the output I get, is a functional of the initial input, which is bt. Is a functional, not a function. In some cases, we will see that it is a function. But in general, it is a functional. Right? It depends on the whole trajectory. Right? So xt is, there exists some functionals in some infinite dimensional space, such that this xt is this functional of the whole path up to times t of this bt.
Global in some sense.
Huh?
It's global in some sense.
Yeah, global, yeah. Here I have global solution up to infinity. If I take t to be, if I take capital T to be plus infinity, I have the solution.
No, I mean global on all t, not t that times small t.
Yes, no. At each time small t, my solution is a functional of b, s less than t.
Small or capital?
Small, yeah, up to small. Okay? So this, let's go over some examples first, and then we will go over the proof. So this result I showed you can be extended to higher dimensional. This means that the Brownian motion can be in RD, the coefficients can be matrices, can be whatever, okay? This B and sigma can be a matrix, and B can be a vector. Okay, so let's start then with these examples. So the linear conditions ensures the solution does not explode, right? This is what we know in theory of differential equations always. Once you have the linear growth conditions, so your solution will not explode up so on the 0t, for example, or 0 infinity. Consider this example. The xt over t is xt squared. This is a deterministic equation, right? And the solution is given by xt is equal 1 minus t, right? And this diverges when t is equal to 1. Why? Because it's not of linear group. It is of quadratic group. Okay? So the Lipschitz condition, what does this ensures? So consider this deterministic equation. dxt over t is equal to 3xt to the power 2 over 3. Initial condition is equal to 0. Then the solution is given by this equation. You have infinitely many solutions. So the Lipschitz conditions led to us to get unique solutions. Once, yeah.
So from this example, you mean that when the function is only ordered, we cannot get the uniqueness?
we can get uniqueness in some cases.
Yeah, because I have seen some paper when we have the uniqueness with holder.
Yeah, holder less than 1 is okay.
Yeah.
Right? Holder less than 1?
Less than half, no, or greater than half.
Greater than half, it could be, but less than 1.
Yeah, it should.
Yeah, it should be less than 1, right? Okay, so this is one situation where you have this, and so here B, you have B is T3 x to the power 3 over 2. It does not satisfy the Lipschitz condition because the derivative is not bounded. Right? Okay, so if we consider now the stochastic version to that one, we add this perturbation here. This is now the diffusion coefficient, and this is the drift coefficient. X to the power 1 over 3, the diffusion coefficient is x to the power 2 over 3, and in integral form we have this. So the solution to this equation can be obtained by choosing just this formula, which is the solution to the deterministic equation here. You see here above. And now for x greater than a, it is x minus a to the power 3, which is the case here, and 0 outside, right? Now if I apply the Ito formula, if you remember the Ito formula, take the first derivative of this function. It gives you 3 theta of a x to the power 2 over 3. And the second derivative is 6 times theta a of x to the power 1 over 3. Right? So now if we substitute, if we use the Ito formula, this is the first application. The Ito formula of that one, we get exactly this one and we get this. What does this mean? This means that theta of a of b is a solution to this equation, right? To this equation here. So this means that you have infinitely many solutions. This is the deterministic case, and this is the stochastic case, right? So because we don't have our Lipschitz properties here. So in general, let me recall that once you have b and sigma differentiable functions, the Lipschitz property implies that the derivatives, partial derivatives relative to space of b and sigma are bounded by constants d and d1 and d2. Okay, another second application of the Ito formula is once you get this process of this form, xt is equal to x naught exponential mu minus sigma squared over 2 times t plus sigma wt. So now we apply the Ito formula. The stochastic, applying the Ito formula, you get exactly this linear equation, right? Okay, so you have always this correction term. So we have to remember in stochastic differential equations, there is correction terms here. If sigma is equal to 0, you have the linear without this sigma, right? So this is the correspondence between those two solutions, and the Ito formula is to have to solve this problem. More generally, if I have time-dependent coefficients here, b depends on time and sigma depends on time, then the solution is equal to xt, x naught exponential, integral from 0 to t, bs minus sigma squared, s divided by 2 ds, and then the integral with respect to the Brownian motion. So this has many applications in finance, in pricing, financial instrument, financial derivatives, and then this is called the Black-Scholes formula, the Black-Scholes equation. There is another interesting problem also dealing with in population dynamics. You can recognize some forms here, this linear equation, and you have constant perturbation on of this equation now in front the Brownian motion. So you can, if your equation is modeled by this equation right here, you have explicit solution and so on. And now sometimes you have some formulas that are motivated by these perturbations, considering this linear form. How to solve this equation by using the formula? It is very simple. Just you consider the linear part here, dxt is x1 minus a xt dt, right? And x naught starts from x. So of course the solution is xt exponential minus at, right? So this is the explicit solution. And now what we are going to do, I will take this transformation. I will write x, okay? Write x as y exponential minus at, okay? And then I will take this to the right hand side. This means that y is xt exponential 80. And my xt satisfy my initial equation. And using the Ito formula again, this is the Ito formula. Once you apply the Ito formula, you get dyt is equal to this as differentiation. Differentiate this one. And you integrate against this is integration by part formula. It's integration by part formula. And this leads to this equation. Right? So you have no y in the right hand side now.
Yes.
And then you take the integral, just take the integral. So yt is equal to x plus m exponential a to the power at minus 1 plus sigma integral of deterministic object here dbs. So now what I will do to get x is just to multiply by exponential minus at. If you multiply by minus at, you get this. It will get up from here, and then you will, the remaining part is this. So the solution is obtained explicitly in terms of sigma. Okay, so let's go back again here. Once we spoke about solutions here, we see that the solution of this equation now is a function of bt, right? Theta a of bt, function of bt, right? Here also, xt is a solution of this linear equation, is a function of bt, right? Once the parameters depends on time, you have here the solution is a functional of bt, because it depends on the path from 0 to t, is functional. In this case also, in this original limbic model also, you have the path from 0 to t with for which you integrate some weight, the Brownian motion, exponential of as. So it is a functional of time, okay, of bt. It is a functional of the Brownian motion. Okay, there is some other examples where we can use the Ito formula to find the interesting solutions to some differential equations. Like you have here, for example, this 1 minus square root of t. Just take the sign of bt, and this condition should be satisfied here. Otherwise, you will get some problems because bs would not be in this space because bs takes the value in r. Okay, and then you need only to be in minus p minus pp in order to be able to take the square here, square root here. Okay, so as you can see also, Ito formula is to get an equation of xt bt divided by 1 plus t of this form, right? Linear in this one, time dependent here, and also time dependent here in front of the Brownian motion. Many interesting situations. Yes.
Here, in some sense, it's like the ordinary differential equation. You assume some what we call the guess solution, and then you work with.
Yeah. This is in particular. Once I remove the Brownian motion, I get all the results from ordinary differential equation.
I mean, here you say xt has this form. You differentiate using the Ito formula, you get
yeah, exactly. What you can do is you differentiate to get solutions, but you can come back again. You can see that this is the unique solution. This is really xt bt over 1 plus t is the unique solution. Why? We're going to see. We can verify the conditions because we have Lipschitz properties, and 1 plus t is less than 1.
I'm saying if I'm a student, I don't know the form of the solution. I have the differential equation, and I'm looking for the solution. How can I do to get the solution without knowing?
Yes.
This.
Yeah. Sure. Yes. Okay, so let's see how we can solve this kind of problems. Okay, so I will show you the one method to solve this kind of problems. So there are many. There is an interesting model here concerning nonlinear stochastic differential equation. I have B here of the form f of x and x squared, right? This is used in a model in population dynamics, and this has a many interpretations. This constant k is called the carrying capacity of the environment, and beta measures the size of the noise of the system, and so on. So this equation here is not like what I described in the theorem, because it does not satisfy the conditions, but we can solve this kind of problems, and we can have explicit solutions here also. And you will see also that the solution depends on the whole path, because you have here the integral of bs with respect to s from 0 to t, and you have in the upper form here in the numerator you have bt. Okay, so this you have also this power x to the power gamma. What you mentioned, it could be some other continuous coefficients when beta is You have to choose some beta in order to avoid explosion of the solutions. Okay, so you have also some equations with singularity 1 over yx, 1 over x, and so on. Okay, very good. So maybe I have to escape this خمسة. Okay, 30, okay. Maybe I go over quickly. You as professors, you know these results, but maybe I will go just to recall very quickly what's going on. I will use Grover's lemma and so on. So once you have a function f given a function phi in L1, which satisfies this inequality where f is in L1 also and beta is a constant, and the question is, can we estimate this this phi once it satisfies this equation? So what we do in general is we have this inequality, we go to the right hand side and solve the equation as we have a linear equation, and then compare this phi with the solution of the upper bound. This is the idea, right? What we do to solve this problem is to estimate this, I consider the solution of the right hand side. I take a function psi which satisfies this equation, substituting here psi and equal to psi. I force it to be psi, right? So I look to the solution to this equation, and it turns out that the solution of that equation is greater than this one. Yeah, this is mathematics. Funny, right? So g of t is equal to this one. I write this beta integral from 0 to t phi s, right? So once you take the derivative of this, g prime is equal to beta phi t, and it is bounded by this. Check the difference. This is the right-hand term, right? Beta f of t plus beta gt, right? So I bring this one from the left-hand side, take it in the other side to keep f here. So g prime minus beta g is less than beta f of t. So here, what I will do, I will just multiply by exponential minus beta of t. What you get finally, once you multiply this, you get that this is the derivative of the product, right? Exponential minus beta t gt, exponential minus beta gt, right? This is less than beta ft exponential minus beta t. Okay, once you arrive here, you get finally that this is less than this one. Okay, now what I get from g? For g, it is less than beta integral from 0. So I succeed to bound the right hand side of this inequality here, this one, which I called j. I succeeded to bound it by something which depends on f, right? And then what you get finally is a phi of t is less than f of t plus g of t, and then this is exactly f. So everything here, the right hand side, there is no phi at all. So this gives nice properties. Okay, now the result is that the Bellman-Grovel lemma is this one. Phi of t satisfies this inequality, phi is in 1, then you have the conclusion here. Applications, once you take ft as a constant, alpha, you get the bound uniform in time here of phi t, which is alpha exponential beta t. This is also interesting. Once you have alpha is equal to 0, you get uniqueness, right? Phi equal to 0 for ht, then you have uniqueness. This is one important thing. What you need this for a uniqueness. And the second one, we use it for existence. Okay, for existence, let's consider that you have a family of L1 integrable functions in L1, which satisfies similar inequality to the previous one, but there is only some iteration here. You have n plus theta of n plus 1, and it is on the right hand side you have an integral of theta n. Okay, some induction formula. And f is always in L1 and beta is greater than 0. So if we iterate this step by step, this is for our students, right? Theta 1 is less than this one. And theta 2 also, yeah, theta 2. We have this. For theta 3, we iterate. We have theta 2 here. And we replace theta 2 by this estimation here. And then we get this one in terms of theta 1. Okay, continuing this, we get this kind of equations. Okay, let's see what happens for any n. For any n, you get this bound here. Theta n plus 1 is less than this. And you have some integration here, which is funny, which leads to some series, right? So you see here that some series appeared here. Okay, if I take, for example, a supremum here of this quantity on u, it will be outside, and then you get the integral of theta 1. So I can bound this summation by exponential, right? This is the development of exponential, right? This is less than this one. So you conclude immediately that you can bound these terms here in front of f and in front of theta. You can take it as it is. You can keep it as it is, but you substitute here. Okay? So you get at the end this result here. Once you have this family of functions satisfying these inequalities here, what you get at the end is the theta n plus 1 can be bounded in this term, which is very similar to the Bellman inequality, right? Plus this term here, right? So one should be able to control very well this term. And what about applications? Once you take of t a constant, alpha, and you take theta 1 is a constant also, so you get something which is interesting here. Theta n is less than something which depends on time, so you can take here capital T and you have uniform bounds, and you have some series here which is exponential. The series is convergent, so this leads to interesting property. So this is what we need for existence.
What's the name of this?
And I think that this lemma is called also Granville's lemma, corresponding for sequences. Yeah. Okay, so let's now see how to solve these equations. Once sometimes we don't have explicit solutions, so we just try to prove if there are solutions. So let's start by, this is my x0, xi is my x0. This is the integral equation I want to solve. My conditions on B and sigma are linear growth condition and Lipschitz condition uniformly in time. Okay, so the result is we have unique solutions once we assume that xi is a random variable which is square integrable. And okay, let's start with uniqueness. What we do, we take two solutions, take the difference, and get estimation. That's very easy, right? So take xt and y be two solutions, and then z is the difference. So if you write the difference here, xi will simplify, and you will get two integrals, right? One with respect to ds and one with respect to db. In db you have sigmas, and in ds you have the drift coefficient b, and then you use this very simple inequality, a plus b squared is less than 2a squared b squared. Convex inequality, right? Okay, once you do this, you get z squared. Everything is random here. I just take the random here, square times the square of the stochastic integral part, the square of the deterministic part. Okay? Later, for the first, where you have stochastic integral, then I take expectation. I take square, and second step, take expectation. Once you take the expectation, you want to get expectation of this integral square. But we know that this is a stochastic integral equation, and we have the formula.
The expectation preserves the order.
Huh?
The expectation preserves the order. Less than or equal to.
Yes. Yeah. Respect the order. Yeah, it's increasing the operator. So here you have the isometry, what we call the isometry property. The expectation of a stochastic integral square is equal to the expectation of the square inside, and you take with respect to ds. So the dbs disappears. And now use here in this step, use Lipschitz condition. When you use Lipschitz condition, you get something d1 xs minus ys, which is zs. Then you get here chi squared zs. My k here is a constant which changes from line to line in order to be able to. So here in this step, I just use Holder inequality. Holder inequality, so you have time here, and then you have integral, and take the square inside. I take capital T here, k square. This is also Lipschitz condition on B. You have z square. Now I take expectation. If you take expectation in this, you get this inequality for both. I add this one with the second one. So I get then expectation of z square is less than this constant. Expectation of z square integral from 0 to t. Expectation of z s square ds. This is Bellman-Granville lemma, which we have proved already before, and you have this alpha is 0, beta is this constant. So once you have alpha is 0, you have z is equal to 0, right? Thanks. Go back to this estimation here. Where is the lemma? This one, right? Alpha is 0. You have beta here, exponential beta, but alpha is 0. So you have phi is 0. Okay? So let me mention something which is interesting here. This is interesting. What I wrote here, almost surely. But I have just expectation of z squared is equal to 0, right? That's what we have. Expectation of zt squared is equal to 0. You have, this means that xt z squared is equal to 0 almost everywhere in omega. This is a measurable function, right? My small omega, so this is almost everywhere in omega. But the problem is this almost everywhere. It depends on t.
Yeah, almost sure for omega, not for t.
Yeah, yes. This one, yeah. This one is equal to almost surely
On omega.
on omega, right? Right here. Okay, t is fixed, right?
Yeah.
So what does this mean? This means that the negligible set depends on time.
Yeah.
For fixed t, there exists a negligible set which depends on time, for which the probability of this set is equal to 0. But this time t runs over continuum of interval, continuum interval with 0 to capital T, which is not countable. So this negligible set, if you get the union, is not measurable. You don't know, right? Okay. So what is the key? The key is the regularity of the solution. Because I have given in the definition that my solution is continuous. We can prove that the solution is continuous. Once you have the continuous on time, you can construct a negligible set by density. Because Q is dense in R, and then you take this argument to prove this equality is almost sure. So this is almost sure in time and almost everywhere, almost sure in omega and almost everywhere in t. So this means that this is a nil process. When can we say that stochastic processes are the same? Or let's say when a stochastic process is equal to 0. If you say that for every t, xt is equal to 0 almost everywhere, this is too much. Sometimes this is too much for you. You may get something which is more flexible. This is the existence. So, of course, for the uniqueness, for existence, you know that iteration process is equivalent to fixed point theorem. I will here adapt iteration, Picard iteration scheme, because it does not require many techniques or many calculations or many big theorems. But it is possible to prove this result using fixed point theorem. Define the appropriate functional space, and then you prove that you have a contraction and so on.
I have one question, please.
Yeah.
For the Bellman-Grommer inequality,
Yeah.
here you use the classical one.
Yes.
Yeah. So, but my question, is there any Grommer inequality with not with the dt?
The bt?
Yeah, dt.
No.
It cannot be.
Unfortunately, no, because we have no monotonicity with the because it fluctuates a lot. There is no sign. You cannot have inequalities. You have always to kill randomness to get back to deterministic inequalities. But you have the moment inside. We had this inequality, you see. Expectation of z. This is my phi t.
Yeah.
Okay? Otherwise, we don't have order. Okay, so this is okay. This is uniqueness. Existence is a simple iteration scheme. Start from x1 equal to xi, and xn plus 1 is the iteration, right? Now let's see. Now x1 is equal to xi, right? This x1 lies in it is adapted to the filtration of the Brownian motion, and it is square integrable, it satisfies everything, right? And it is continuous in time, because it is constant. Let's see now what happens for theta, for x1. For if you want to say what happens for this one, assuming that this one is regular, now assuming that x1 lies in L adapted, is adapted and square integrable, and satisfy this equation, this inequality for x. 0 to capital T expectation of x as ds. Okay? So once you do this, you just use linear growth conditions to estimate this integral here, expectation of 0 to capital T sigma square. I know with linear growth condition what you have. You get this one, right? By linear growth condition. I have here a constant and I have expectation of this one. So my hypothesis induction property, I assume that this is finite, right? The same for B. What happens now for xt? Now, once you have this, xt is continuous because it is the integral of something which is continuous, right? So this is very easy. Moreover, it is if adapted because everything is adapted here. You just take a position, and using this inequality here, you get that the moment the xt n plus 1 square is less than these three terms. And once you get the estimation here, you just get estimations. We have already estimations from that one. Because this is linear growth condition, this is linear growth condition, and then we end up with the property satisfied for xn plus 1, right? Yeah? Now we have to estimate the difference. This is our theta n. This is my theta n is the difference now. I take the difference between two approximations. And this is what I call y, the first integral, and zn, the second integral with respect to ds, and this one with respect to dbs. So I can split xn plus 1 in three terms. You have constant xi here, you have yn plus 1 and z1 plus 1. You take the difference, you use classical estimation, and then once you arrive here, okay, we have the difference between for y and the difference for z. If you estimate this square, this is equal exactly for y because it is a stochastic integral. This is equal to expectation of sigma corresponding to n and n minus 1 in the other side here in the other term square, right? So here you use just Lipschitz condition. You get the difference here xn minus xn minus 1. For z the same, you get also the difference. So what we end up finally that the difference between xt n plus 1 minus xtn is controlled by constant integral from 0 to small t expectation of xn s minus xns minus 1. This is my theta n. This is theta n plus 1. This is theta n. Exactly I am in the situation. And for the last one here, we should compute for the first difference. This is finite. So we end up finally by this difference here is controlled by rho beta to the power n to the power n divided by factorial n. So since you have this series is convergent, there is a result in analysis which says that once you have this series is convergent, you have this series is convergent. So this means that it's in convergence in this space in L201. So this is mainly what we have. So I will skip these details here. And just to tell you that what I mentioned now is once you have this series is convergent, right? So this means that xn converge, right? Using this property. Okay, this one. Take the norm here. This is less than the norm of this one and less than the norm of that one. And the norm of this one is less than the series. This is converges, so xn converges. That's the job. Once you have here xn converges uniformly in probability to some stochastic process I denote by xt. So the uniform convergence informs me that xt is continuous and it is adapted to the filtration of B, the Brownian motion. Moreover, I have this estimation. Take the limit here, so you have the norm of x is less than the norm of psi2, less than the square root of this series, which is convergent, right? Okay, so this means that the integral from 0 to t, expectation of 0 to capital T xt squared dt is finite. That is what is required for the solution. So the conclusion is our limit is adapted to the solution. So this is the existence result for this problem. Okay, now once we have the convergence passing to the limit in the equation, let's go back to the equation of xn plus 1, the iteration scale, Picard's iteration scale. So the convergence term by term now. So then xt satisfies this equation, so this is the existence result for this kind of of equations. You asked me one interesting questions, how to recognize those forms of the solutions I presented before, because it is very easy to verify the equation rather than to solve it back. Okay? So let's see how one can deal with this kind of equations in order to be able to solve those problems. So the first thing is, one method is I assume that my initial equation has a solution, right? Then I take this equation and transform it by another equation. Let's say u of xt. I use Ito formula. I suppose that everything is regular. I use Ito formula and I get a decomposition, right? Yeah, I will get something which contains stochastic integral and deterministic integrals. Then I can, for example, force my second new equation to be independent of the drift. Means the term on ds is 0. So this will be removed. And I can choose my u in such a way to get some easier forms of that new equation. This is the idea. One method to solve this one. Another one is to make some transformations to forget the stochastic part, to cancel the stochastic part, and only you have the remaining object for you is the deterministic part. Then you solve it by the methods you know, and then try to be back. Okay, let's see what's going on.
Some change of variable.
Yes, exactly, some change of variable. So we consider this equation here. We have f here, and you have some form here in the drift, right? ct, xt. So where these functions c and xt are deterministic, satisfy some Lipschitz condition, and so on. So what can we do? We use this transformation. xt is equal to ft times yt. And ft is this equation here, is this exponential. Because, why I take this one? This means that I forget this one, because this one is not linear, it is complicated, right? Non-linear part. So I forget this one, and I take the linear part. So for the linear part, I know the solution. If you take f is equal to 0, the solution is exactly this one. متفقين؟ كويس. Then, this is the transformation I told you. So I put x. This means I look for a solution which is a multiplication of the linear part with something. Let's try if I can find the solution of that form. I force the solution to be on this.
In some sense, like in the ordinary
Yes,
differential equation, you take the particular form, and then you assume that instead of the constant, you take function. You differentiate.
Exactly. Yeah, and you differentiate, you see what's going on. Yeah.
Using the Ito formula.
Yeah, the key is the Ito formula now. Everything with stochastic is the Ito formula, which also is true also for deterministic equations. So once you take here the Ito formula of x here or y here, so you have y dy satisfy this equation, ft minus y dt. This is a deterministic, right? There is no stochastic here. Right? The stochastic only comes from this f. But once you have this means that an ordinary differential equation with stochastic coefficients. Randomness also in the coefficient. The difficulty once you have here, the randomness comes from the integrator here. Because here we can solve everything path by path. We fix omega and solve the problem, and then the result it does not change. Okay? So this is an ordinary differential equation with random coefficients. Okay, let's see what happens if I take this form. If my f takes this form, f of t yt dt, right? F of t times x. So my equation can become this one.
The Black-Scholes, no?
Yes, exactly. Yeah, the Black-Scholes now. This is the Black-Scholes equation, and then the solution is exactly this one. The product. This is the product. This is the first part, and this is the second part. All are exponential. Okay. Other forms can be also general linear equations. I have multidimensional now. Multidimensional. It is also possible to solve this by using this transformation here, xt ut vt. ut corresponds to the linear equation here, linear part, right? Because I have here, linear here, but I have some other coefficients here, a and b. This is what disturbs my equations. This is not, I am unhappy with these terms, right? So what we do is we take the corresponding solution to the linear equation, which is u, because we know the solution for this one already, right? This is the Bloch-Scholes equation. U is this one, with this correction term here, d. And now dv is alpha beta, with alpha beta. Okay, this is an integral equation, right? Now differentiating between the two equations, the product here, we just get the beta t is equal to ctu minus t, and then finally you get your xt is ut plus this times these equations, right? Because now it is there are vectors here, right? Because a general linear equation could be whatever, right? So this is what you mentioned for Holder coefficients, and the Holder coefficient is greater than 1/2, right? So the stochastic equation now for this order has a unique solution, right? For r greater than 1/2, and this is a model which is called Cox-Ross-Ingersoll model, which is very used in financial modeling for interest rate and so on.
By the way, I have one question.
Yes.
Your assumption is on the stochastic coefficient, GC.
Yes.
Remove your stochastic.
You mean her ds?
Yeah, ds.
Okay.
With your r greater than or equal, half or whatever. Is there any uniqueness of the solution?
There is unique solution when you have for deterministic.
No, deterministic even.
You have infinitely many solutions in this situation. I don't know if I have it in the slide here. We have it in another folder.
Yeah, I mean the holder is on the drift, not on the stochastic.
I know.
Yeah.
I know what you mean. I know what you mean. In this situation, you have bifurcations. You have infinitely many solutions. I don't know if let me show you the file if I have it in my flash here. I hope so. So this is, by the way, almost the end of the talk. The end of the talk. So let me show you if I can have access to